the TAC login issue channel, and then we will take a look at that during the lectures, okay? So otherwise, now it's time to leave the room to Roxana.
Okay, so can you hear me well?
Yes.
Let me just change to full screen. Okay, you can also see my mouse.
Yes, all good. Thank you, Roxana.
Okay. Okay, thank you, everyone, and yeah, good morning, good afternoon, and good evening, and thank you for participating to the second day of our school. As Feliciano said today, I'm going to describe another capability that is implemented in the EPW code, and this is the methodology for computing superconducting properties with the Anisotropic Migdal-Eliashberg formals. So to get started, I'm just going to give you a brief overview of superconductivity milestone. So as you can everybody know, probably, superconducting materials exhibit zero resistance to electrical current when cooled down below a critical temperature. And this was first observed by Ons back in 1911 in mercury, when in solid mercury, when cooled down below 42 Kelvin. Since the discovery of superconductivity over 110 years ago now, a substantial effort has been devoted in finding materials with even higher critical temperature. And the reason why we want materials with larger TC is because for widespread applications, superconductors must be able to operate above 77 Kelvin, which is the boiling temperature of liquid nitrogen. And also we want these materials to be easily manufactured into wires. So the next breakthrough in superconductivity research was the discovery of copper oxides in 1986, and this was a new class of superconductors. And I'm not going to go into details. I should have mentioned that the first class is phonon-mediated. These copper oxides are unconventional superconductors where the superconductive mechanism is not driven by phonons. And the critical temperature in these materials soon after their discovery exceeded 77 Kelvin. So it was really thought that this is going to bring a revolution in terms of technological developments, but unfortunately these materials are ceramic and they cannot be easily manufactured into wires. Another breakthrough in superconductivity research was the discovery of a high TC superconductor in the phonon-mediated class, and this was in a well-known compound, magnesium diboride. And this basically triggered a lot of research, especially in phonon-mediated superconductors, because it gave hope that materials with even higher TC can be found. The next major discovery was, again, a new class of superconductors. In this case, it opened what is called the Iron Age. These are the iron peptides. They are also unconventional superconductors, and have a TC that can reach even 100 Kelvin. And finally, I would say the latest milestone was the discovery of, again, phonon-mediated superconductivity, but in this case, under extremely high pressures at about 150 gigapascal with a critical temperature of around 200 Kelvin in a sulfur hydride. I should also mention briefly that in the last few years, there have been reports of room temperature superconductivity achieved either at very high pressure, around 207 gigapascal, in a compound made of carbon, sulfur, hydrogen. And this year, even a room temperature superconductor near ambient pressure was reported in a nitrogen-doped lutetium hydride. But these experimental findings have not been confirmed by other groups, like other experimental groups, or even back up by theory. So this is basically, I would say, what has happened on the experimental side in terms of finding new classes of superconductors. So now let's see a bit what has happened on the theory side. So the first microscopic theory was proposed by Margine, Cooper, and Schiffer, and this is referred to as the BCS theory. And this starts from the assumption that there must be some attraction between electrons that which can overcome the Coulomb repulsion. And in conventional superconductor, the attraction is mediated by phonons, so it's what we call an attraction due to electron-phonon coupling. And this can be illustrated in this diagrammatic representation. So basically, what happens is that two electrons scatter on each other by exchanging phonons. Yeah, so two electrons of opposite momentum and opposite spin exchange a phonon, and they scatter at the new states, K prime and minus K prime, again with opposite momenta. And for this scattering to take place, it means that the final state, K prime minus K prime, need to be in the vicinity of the Fermi surface. Need to be in the vicinity of the Fermi level, which is the highest occupied energy state in a metal at room temperature. So the BCS theory predicts the formation of a gap in the band structure of a normal metal, and this gap has temperature dependent. So now, while electrons are fermions and they must obey a Pauli exclusion principle, this paired electron, which are called Cooper pairs, they have boson-like properties, and therefore they can condensate on the same energy level. So basically, because of this condensation, this energy gap can form, and as you can see, there is an increase in the density of states at the lower edge of the gap. And this increase in the density of states occurs because the electrons that have initially occupied the states within the gap now occupied the state right at the edge of the gap. So this temperature-dependent superconducting gap in the BCS model can be found by solving the BCS, this equation, where here delta labels the superconducting gap, V is the pairing potential, and this E is the quasiparticle excitation energy, which depends on the superconducting gap delta and the normal state eigenstates epsilon and k with respect to the Fermi level. So if you solve this equation at various temperature, you will find a plot like this, where the maximum value of delta happens at 0 Kelvin, and this temperature, this gap becomes 0 at the critical temperature Tc. So beyond the Tc, as you can see, there is no gap. So the system goes back to the normal metallic state. So the BCS theory has been described in detail, the phenomenology of superconductivity, but it still remains a descriptive theory in the sense that is material independent. So it predicts this equation for that relates the gap at the 0 temperature with the critical Tc. So basically it has this equation with this factor of 3.53. And more importantly, the BCS only works for weak electron-phonon coupling and treats the electron-phonon interaction as instantaneous. So in other words, it does not account for the retardation of the electron-phonon interaction. So now, after this introduction, now let's see how, in fact, we can compute nowadays the critical temperature beyond the BCS theory. And for many years, the vast majority of calculations have relied on the McMillan formula, which was later modified by, refined by Allen-Dynes. And this is what it is referred to as the Allen-Dynes expression for the critical temperature, where the key parameters that enter here are the omega log, which is a logarithmic average of the phonon frequency, lambda, which is the strength of the electron-phonon coupling. Yeah, so this expression we can find here. So it's an average, double average of the Fermi surface of the electron-phonon matrix elements. So it basically accounts for all possible scattering processes between states k and k plus q through a phonon of frequency omega q nu. And mu star, this basically is a semi-empirical parameter called the Coulomb pseudopotential, which describes the Coulomb interaction. So the reason why this approach has been so popular is that the key quantity, the electron-phonon coupling strength, could be easily computed with quantum espresso rabbinic codes. It was also found that it works quite well for isotropic superconductors, yes, so for simple metals. But as you can imagine, it fails in the case of multiband or anisotropic superconductors, for instance, such as MgB2. And as I said, it approximates this Coulomb interaction through a parameter mu star, which usually takes a value between 0.1, 0.15, or 0.2, or it's fitted to match the experimental TC. For the, I would say the next 20 minutes probably of my talk, I'm going to show you how we can derive the anisotropic Migdal-Eliashberg equation. And in fact, I should have mentioned that the TC expression, this TC expression, is based on a solution of the isotropic Migdal-Eliashberg equations. Yeah. So now, basically, so in 1960, Eliashberg proposed a generalization of the BCS theory that incorporated the time-dependent electron-phonon interaction formulated by Migdal for the normal state. And all relevant quantities that govern the superconducting pairing can be computed in these Nambung-Gorkov-Green's function formulas. So in these formulas, a generalized 2x2 matrix Green function is introduced that can describe the propagation of electron quasiparticles and of the superconducting Cooper pairs on an equal footing. Yeah, so as you can see here, the Green's function looks pretty similar to the expression shown yesterday by Feliciano. The only difference is that right now we have a 2x2 matrix. So here, tau is again the imaginary time, and t tau is the Wick's time ordering operator, and psi here is a field operator. But this field operator right now has two components. One component is the annihilation operator that annihilates or destroys an electron in a state with momentum k and spin up. And the second component is the creation operator, which creates an electron in a block state with momentum minus k and spin down. So if you just, and this average basically represents an average with the ground state of the system. So now if you plug in this two-component field operator in this expression, and you just basically do a multiplication of two vectors, column and a line vector, you will get a 2x2 matrix. Yeah, so in this case, the diagonal components are called the normal state Green's function and describe single particle electronic excitation. And you can see there is the annihilation and creation of an electron in the same state, yes, momentum K and spin up, while the off-diagonal elements describe what is called the anomalous Green function, and they describe Cooper pair amplitude. So as you can see here, we have the annihilation or the creation of two electrons with opposite momenta and opposite spins. Since this generalized Green function is periodic in the imaginary time, it can be expanded in a Fourier series, as you can see here. So in this case, this I omega j, these are fermionic Matsubara frequencies, and T is the temperature. Yeah, so from here, we have, by doing this transformation, we have frequency dependence and basically temperature dependence. And again, just here I'm just showing the labeling. It's traditional to label this anomalous Green's function with letter F. So now let's see how, using this formalism, the generalized Nambu-Gorku formalism, we can obtain the anisotropic Migdal-Eliashberg equation. And in order to do this, we need to start from the pairing self-energy. So the pairing self-energy, as you may recognize, looks very similar to the expression that Feliciano showed yesterday in the normal state. But again, now here, both the pairing self-energy and the Green's function are 2x2 matrix elements. Yeah, so the first term describes the electron-phonon interaction, and is nothing else. It's similar to the Fan-Migdal self-energy, while the second term describes the electron interaction, and it's basically similar to the GW self-energy. So one thing that you may notice here, that I made an approximation, so I'm only considering the static screened Coulomb interaction, as there is no frequency dependence. You can derive the equation while you can keep the frequency dependence as well, but for simplicity, I'm just working in this case in the static limit. Another thing that I should mention, why this is called, this self-energy expression is called basically the Migdal-Eliashberg theory, because it relies on the Migdal's approximation, which ignores electron-phonon vertex correction for the electron-phonon interaction. So in other words, the Migdal's approximation rests on the assumption that the neglected diagrams are of the order of the square root of the electron mass over the ion mass, which is proportional to the ratio of the Dubay frequency to the Fermi energy. Yeah, so in general, this ratio is very small because the Dubay frequency is of the order of 100 milli-electron volts, while the Fermi energy is of the order of 10 electron volts. Yeah, so of course, for superconductors in which this ratio is large, where the phonon and the energy scales are comparable, the Migdal approximation may break down, and in that case, electron-phonon vertex correction may could play an important role. So now, I'm just rewriting now, converted this diagrammatic representation in a full expression for the electron self energy. And the first step is to replace the dressed phonon propagator by its bare counterpart. So again, this is an approximation, so which means that any renormalization of the phonon frequency or any line width due to electron-phonon or phonon-phonon interactions are neglected at this point. And by introducing this bare phonon propagator, now we can define what is called the anisotropic electron-phonon coupling strength that, as you can see, connects the bare phonon propagator with the electron-phonon matrix elements. So if we plug this lambda in the expression for sigma, we arrive at the following equation. So it doesn't seem that we have made much progress so far, and what we need right now is basically to impose some self-consistency on this equation, and to do that, we need to find an expression for the Green's function. And to do this, we can remember that the Green's function obeys a Dyson equation in Matsubara space. Yeah, so this is the Dyson equation. I think we also saw an expression like this in yesterday's lecture by Feliciano. And G naught is the non-interacting Green's function. And in this case, I just express it in terms of Pauli matrices. And the electron self-energy in Migdal-Eliashberg formulas, it is commonly expressed as a function of 3 scalar functions, also as linear combination of Pauli matrices. And in the next few slides, it's going to become more obvious why these scalar functions are introduced. So in this case, Z is the mass renormalization function. Again, an analogy with the normal state. Chi is just a shift in the energy, and delta is the superconducting gap function. So if we replace or if we introduce these 2 expressions for the non-interacting Green's function and for sigma in terms of Z, chi, and delta in the Dyson equation, and then we do and then we invert this matrix, we will get the following expression for the 2x2 matrix, 2x2 Green's function. Yeah, so I'm just here to remind you, as you can see, the diagonal elements only depends on quantities in the normal state, yeah, Z, and basically this energy shift, while the off-diagonal elements depend on the superconducting gap. So what is important is that these off-diagonal elements are different than 0 only below the critical temperature. Yeah? So beyond Tc, they become 0 and basically showing the transition to the normal state. So, so the next mouse is not working very well. So the next step we can this is the same expression as on the previous slide. The only difference is right now I just wrote it down in a more compact form in terms of the Pauli matrices. And we can now remember the reason why we wanted this expression is to have an expression for G that we can plug in the expression for the self-energy. So if we do this, we arrive at the following expression for the self-energy. And then the last step here is to equate the scalar coefficients of this 2 expression for the pairing self-energy. And this is going to give us 3 equations. Yeah, you see that we have the coefficients of tau naught, tau 3, and tau 1. Yeah. So once we do this final step, we arrive at what we call the anisotropic Migdal-Eliashberg equations. And we call this equation the full bandwidth because there is no restriction for the electronic states to be right in the vicinity of the Fermi surface. And this equation will need to be solved self-consistently. And they are also supplemented by another equation for the number of electrons in order to determine the Fermi energy. Just one thing that I guess I should mention here is that you can see that the Coulomb interaction only enters in the expression for the superconducting gap. And the reason for this is because we only keep the off-diagonal contribution to the Coulomb self-energy in order to avoid the double counting of Coulomb effects. In fact, if we would have worked with a dynamical representation of V, then you will have had also a term in Z and chi. So, this full bandwidth set of equations have been recently implemented in EPW, and one of the exercises today is going to show how the solution of these equations. But in many cases, you don't need to solve the full bandwidth anisotropic equation, and instead you can solve what is called the Fermi surface restricted equation. So those are obtained by making the assumption that the superconducting pairing only occurs within a small Fermi window around the Fermi surface, and that the electron density of states in the vicinity of the Fermi level is assumed to be constant. So under these two assumptions, we can perform an integral over the Fermi surface. And in that case, you can find that chi vanishes. And the equation for the particle number is fulfilled automatically. So now this is slightly cheaper computationally, and this is again these two equations are implemented in the code. So the key quantities that you need to basically you need to obtain when solving the anisotropic Migdal-Eliashberg equation in either the FSR or the full bandwidth approach are the is basically the anisotropic electron phonon coupling strength, which is obtained based on the electron phonon matrix elements, and that's where EPW, the implementation of the Vanier Fourier interpolation technique in EPW is very efficient. The second quantity is the Coulomb matrix elements, but while in principle it is possible to calculate this ab initio using GW codes like BerkeleyGW or Sternheimer-GW, in practice, it is common to replace this Coulomb interaction with a semi-empirical pseudo-potential based on the moral Anderson model. So that's basically the current implementation in EPW. The Coulomb interaction is replaced by the semi-empirical parameter mu star that the user can provide. But in a few studies in recent years, we also computed mu as a based on electron phonon matrix elements found with Sternheimer-GW code. So in this case, you do a double average over the Fermi surface of the electron phonon matrix element to get the mu, and then you screen it down to the level of the Fermi level using this moral Anderson pseudo-potential. So just kind of to summarize here, so this equation, the anisotropic Eliashberg equation, need to be solved self-consistently at each temperature. The equation must be evaluated on dense electron and phonon grids to properly describe anisotropic effects. And the sum over the Matsubara frequency, while it is infinite, in practice, it must be truncated. So a typical cutoff is of the order of 1 electron volts, or let's say about 10 times your largest phonon frequency in the system. And if these equations are solved in this Fermi surface restricted version, you need to keep into account that Z and delta are only meaningful for states at or near the Fermi surface. So it doesn't make sense to have a very large Fermi window when you compute these quantities in the full Fermi surface restricted version. So, this Migdal-Eliashberg equation on the imaginary frequency axis, basically on the Matsubara frequency axis, are computationally efficient, and they can be used if one only needs to obtain the superconducting critical temperature and the superconducting gap. But if, for instance, you are also interested in finding some information about the spectral properties, like the quasiparticle density of states or single particle excitation spectrum, then you need to have you also need to be able to solve the equations on the real energy axis. And while in principle this can be done directly, what we have implemented in EPW is that we do an analytic continuation from the imaginary axis to the real axis using Pade approximants or an iterative procedure. In fact, I should mention that the iterative procedure is only implemented for the Fermi surface restricted approach, but it's very heavy computationally. So I always recommend to use the Pade approximants, which in general works pretty well. So I think that's what I wanted to say about the Migdal. Sorry, there are a few more slides. So now that we have the quantities on the real frequency axis, we can, for instance, look at the excitation spectra by, if, for instance, we look at the poles of the diagonal components of G. Yeah, so if we take the diagonal, one of the diagonal component of G, this will be G11. The poles of these functions give the elemental excitation of the superconductor. Yeah, so again, this is something that you've seen yesterday, and since now we have a complex pole, we can the real part will describe the quasi-particle energy renormalization by the superconducting pairing, while the imaginary part of E and K describes the quasi-particle inverse lifetime due to the superconducting pairing. For the case when at the Fermi level, you see that the energy eigenvalues are basically equal to the Fermi level, this first term becomes 0, and then this equation allows one to identify the leading edge of the superconducting gap, delta NK. Yeah, so this equation is basically, it's only satisfied for very small energies, which are the leading edge of the gap. So this energy is nothing else but the binding energy of electrons in a Cooper pair. Yeah, so if you compute this energy with EPW, this is basically the results shown here in the case of MGB2. And as you can see, we right away get the two gap, the famous two gap structure of MGB2, where the lower gap is due to the pi bands and the upper gap is due to the sigma states present at the Fermi level. As I said, we can also compute the superconducting quasi-particle density of states if we use the imaginary part of the diagonal Green's function. And so this is, for instance, again, the quasi-particle density of states in the case of MGB2. So as you can see here, there is a gap around the Fermi level. And this is the gap due to the pi states. then we have an additional gap since MgB2 is a two-gap superconductors with due to the sigma states. And this quasi-particle density of states were computed for different temperatures, and they can be compared with experimental data. This is not implemented in EPW, but in principle can be easily done. We can also compute, for instance, a spectral function, and that's the spectral function in the case of calcium C6 in the normal state. You cannot see here very well, but this is a continuous line, while if you compute the spectral function in the superconducting state, you should see that here there is a small band gap opening. Yeah, there is too much black here, but you can see here it's a small parabola if you zoom in, and there's a small gap. So that's what I wanted to mention about the Migdal-Eliashberg formalism, but I should just mention briefly that there is another first principle approach to calculate superconducting critical temperature, and this is density functional theory of superconductivity, or SCDFT. So in this case, one needs to solve a BCS type equation where delta again is the superconducting gap function. Z here accounts for the electron-phonon interactions, and this kernel kappa accounts for both electron-phonon and electron interactions. And the strength of this methodology is that it accounts for both electron-phonon and electron-electron interaction on an equal footing. Yeah, so it doesn't make an approximation of the Coulomb interaction as mu star. It is traditionally done in the Migdal-Eliashberg formalism. So for the last, let's say, 10 minutes of my talk, I'm just going to show you a few examples and some outlook of things that lie beyond the implementation or the standard implementation of the Migdal-Eliashberg formalism. So as I mentioned in the beginning, the discovery of superconductivity in MgB2 has triggered or have led to a large number of theoretical and experimental studies striving to find materials with improved critical temperature. And a simple phase in the binary lithium boron system may offer an alternative to MgB2. Yeah, so this compound called lithium boron was predicted was predicted in 2006 by Kolmogorov and Curtarolo, and was synthesized and found to be metastable at ambient pressure in 2015. And the original calculations done on this compound based on the Allen-Dynes formula for the critical temperature predicted a TC in the order of 10-15 Kelvin. So given the close resamples to MgB2, yeah, the only difference is that we have this extra layer of metal atoms inserted between the boron layers. We have recently reinvestigated the system using the anisotropic Migdal-Eliashberg formalism. So in this case, we found that the system should have a multi-gap structure, basically a two-gap structure, similar to MgB2. And the critical temperature in this case, it's approximately a factor of 3, predicted to be a factor of 3 larger than the isotropic case. And in principle, if you do isotropic calculation for MgB2, you are going to find also that the isotropic, let's call it isotropic TC, it's approximately a factor of 2 smaller than the one predicted by anisotropic calculations. So I'm not going to go into details, but we have looked at similar layer compounds. And basically we found that in this layer structure, it's basically critical to compute it using the anisotropic formalism. Yeah? So here in this plot, I'm showing results obtained either with the isotropic Migdal-Eliashberg formalism. So by isotropic, I mean when we take average over the Fermi surfaces, so there is no momentum dependence, or the McMillan-Allen-Dynes expression, and you can see these are lower by a factor of 2 or even more in some cases. And the second example with EPW is a comparison between the full bandwidth approach and the FSR approach in the case of niobium diselenide. So, so the reason why we looked at this system is because below the Fermi level, so the Fermi level is shown here at this dashed line, at about 0.1 below the Fermi level, there is a sharp density of states. So we thought that for this system, the full bandwidth approach may be more appropriate to use because there is this variation in the density of states around the Fermi level. However, since this variation, if we look, it's basically on average, the on average, the constant density of, the average density of states at the Fermi level is basically a good average between what happens above and below the Fermi level. It turns out that in this case, the two methods give very similar results. I should point out here that this critical temperature that we find when only electron-phonon interaction is taken into account, it's approximately 2 to a factor of 3 larger than an experiment, and that's that has been found in other studies as well, and also for niobium disulfide. And I'll come back to this point in the next 2 slides when I'm going to discuss again niobium diselenide. But that's just to show that even for systems where there is a variation in the density of states, unless this happens on a relatively large scale around the Fermi level, a full bandwidth approach may not be necessary. So just let me just mention a few studies, as I said, just to see what lies beyond the standard implementation of the Eliashberg formalism in basically in EPW. And here, for instance, this study done by Davidov and collaborators, they did a comparison between the Eliashberg formalism and SCDFT. So this is not done with the EPW code, just to mention. So what we can see here, that basically in this study, what they did, they solved the isotropic Migdal-Eliashberg equation, and where they accounted for both electron-phonon and Coulomb interaction on an equal footing. And the open dots are experimental data, and this data in blue are calculation done in the static approximation. Yeah, so for the Coulomb interaction, the frequency dependence were neglected. And as you can see here, it was found that it gave a very good agreement with the experiment. Keep in mind that this is a log scale, while when the dynamical matrix elements were taken into account, it was found that the results deviate by about a factor of 2. And this is what they call the weak coupling. So in this case, they didn't take into account the Coulomb effects in the mass renormalization function. And this is a comparison with SCDFT. So as you can see in this case, again, the static result gives very good agreement with the experiment. this dynamic weak coupling where it gives also deviates by a factor of 2, but in the case of SCDFT, the full dynamic effects give also very good agreement with the experiment. Yeah, so the conclusion here is that in the case of the Migdal-Eliashberg formalism, a static, just take into account static effects, gives good agreement with experiment, while dynamical contribution, if you take into account dynamical contribution, the agreement worsens. And the reason for this, the authors explain that it may have to do with the breakdown of the RPA in the W in the Coulomb term. As a solution to this, they proposed what was called the hybrid Eliashberg formalism, where the electron phonon part was computed as before, but the Coulomb part was obtained using an SCDFT approach. And in this case, as you can see, the agreement with the experiment, or the agreement between the static and dynamic contribution also improves. I think I need to move quickly. As you remember on the previous slide, I showed that in the case of niobium diselenide, if we only take into account electron phonon contribution, the superconducting critical temperature is largely overestimated. And this results in the case of monolayer niobium diselenide, which is being considered to be an Ising superconductor, where spin fluctuations can also could play an important role. So so in the study, we incorporated the spin fluctuation effect using a Scalapino's approach. And indeed, we found that if spin fluctuation are considered, the superconducting gap lowers, like it becomes below around 3 Kelvin, 3.5 Kelvin, which is in good agreement with the experiment. So in this case, the roughly two gap structure of niobium diselenide is maintained, but the critical temperature decreases dramatically. Samuel has shown yesterday that anharmonic and non-adiabatic effects are important when you do transport calculation. That's also the case for could be for superconductors. So this is showing a recent study on different phases of solid hydrogen. So in this case, the Eliashberg spectral function took into account non-adiabatic, anharmonic phonon frequency, full anharmonic phonon frequencies, in the sense that it took into account not only frequency shifts, but also line widths. And it was found that the critical temperature when this is considered, can be quite different from this harmonic approach. So for instance, in this case, for this phase of hydrogen, it goes up by about 100 Kelvin at 600 gigapascal, and the same in this other phase, it goes up by an average of 80 Kelvin. Also, as I said here, I can say said that non-adiabatic effects can also affect the electron phonon coupling. So this study has shown that for some phonon-mediated superconductors, the lambda can be drastically reduced when the non-adiabatic effects are considered, and as a result, the critical temperature. Just briefly, since I think Zhenlu is going to talk about this, there is also a question about, for instance, how well the band structure, not only the band structure is described in DFT, but also the electron phonon matrix elements. So Zhenlu have developed what is called the GW perturbation approach and have shown that electron phonon matrix elements in oxides or nickelates can be largely increased when compared to calculation performed with density functional perturbation theory. And finally, I mentioned just briefly that there are cases when electron phonon vertex correction may be important. So in this case, one will have to take into account two phonon scattering processes and basically consider at least the first diagram in the electron phonon vertex correction. And I think Samuel again has shown that this type of two phonon scattering processes have been found to be important in transport calculations. So just to summarize, I would say the take-home messages will be that the Migdal-Eliashberg equation can be obtained from a rigorous many-body framework. And the theory provides a well-defined scheme for modeling superconducting properties for first principle. But you need to keep in mind that the standard implementation of the Eliashberg formulas can be expanded to include additional effects, as I shown here, spin fluctuation, anharmonicity, non-adiabaticity, and so on. And I think I still have a few minutes for questions. Thank you.
Okay, thank you, Roxana, for this wonderful lecture. So now we have time for a few questions. So you will see that in the Q&A there are already 13 questions. So may I suggest that you start answering some of those?
Yes.
Run out of time, you will continue to answer them in writing, okay?
Okay, so on page 4, you demonstrate the electron-electron interaction mediated by a virtual phonon. Is it possible to directly calculate the diagram to investigate superconductivity? So what's the technical difficulty? The Hinder CPW. Not sure I can completely understand the question. This is
yeah, I think that's exactly what is being done.
But that's, I think, what is being done. It's just that we just re-embed that in the other form of the equations. Do we have the Bi-Weller factor term here? Page 8. No, we don't consider this, and I don't think this factor. I'm not sure if this factor will be important in superconductivity. How can I know the Migdal approximation is good or not in different systems? I think one of the rule would be this ratio of the Debye frequency to the Fermi energy. And there are some recent studies that have looked at strontium STO and graphene, where there are very narrow, very flat bands. So that will be systems where Migdal approximation may break down. Okay, now can you please tell me what is the Matsubara space? So this is just an imaginary frequency, the frequency axis. So instead of working on, it allows one to do a Fourier transform from the imaginary time to this imaginary frequency. Do you know any example of material where considering only a small shell around the Fermi surface is not valid and wanted to do a full bandwidth? So some of the hydrides have been shown that this is a case. I can send you a reference. What is meant by two-gap superconductors? So it means that instead of, as I showed in the case of FGB2 and lithium boron, instead of just having one gap around the Fermi level, you basically have two sets of peaks in the quasi-density of states. Is there an unprecedented transition, unbound transition temperature that can be predicted by Migdal-Eliashberg theory? I think there is no upper bound for the transition temperature in Migdal-Eliashberg theory. In principle, can Green's function method be applied to superconducting regimes? I'm not sure I understand this question.
You want to move to the next one?
On page 20, the transition temperature of Nibiru seems not consistent with experimental value. How to explain the discrepancy? It's known. So there are different effects that we are not considered. So first of all, we approximate the Coulomb interaction. There are also non-adiabatic effects that in some studies have been shown to be important in FGB2. How much improvement can we get if we consider full frequency GW approximation in the self-consistent equation? I think the slide from the calculation from Davidov have shown that in the Migdal-Eliashberg case, it seems that the results get worse and you need to do this hybrid approach. Why in the case of a multi-gap superconductor, both gaps close at the same temperature? It's not, this is a self-consistent, it's not possible to have two temperatures. So it's, yeah. Can you go into more detail while the poles of G1, because I thought those quantities are related, sorry. I thought those quantities are related to the self-energy, but here the self-energy is somewhat hidden. Okay, let me go back to that expression. So the poles here, this is the expression for the Green's function. So there is a connection between the self-energy and the Green's function. They are connected to the Dyson equation. So here the poles are only found by taking, basically making this equation equal to 0. Not sure where I was left, sorry. In case of lithium, in case of lithium boron, there is another gap between the two mentioned by 2. Do we not consider that as a gap? Is not why. I mean, if you want, you can say that there were slightly 3 gaps. I would just say that it's just one that is a very strong, 2 that are very marked gaps.
Okay, Roxana, one more, and then we need to move.
Yeah, why does, why the off-diagonal terms vanish beyond the critical temperature? So they vanished below the critical temperature because delta NK, the superconducting gap, becomes 0. Yeah, once you go above the critical temperature, you get back into a normal state where you have a metal, so there shouldn't be a gap.